Hi there and welcome from Ventura, California to today's webinar, High Performance Accelerometer Application in Navigation, Stabilization, Control, and Surveying, sponsored by Inside GNSS, Inside Unmanned Systems, and Thales Group, and hosted by WebAttract, the leader in thought leadership webinars. I'm Lori Dearman, Senior Webinar Producer with WebAttract, and I'll be one of your moderators for today's session. And in just a moment, we'll be introducing our panel of thought leaders as today's webinar focuses on high-performance accelerometers and the burgeoning applications and fast-expanding markets they are opening up. You will also have the opportunity to have your questions answered at midpoint and at the end of the presentation during the Ask the Expert panel session with all four of our panelists today. Now, today we've invited you, along with over 450 professionals registered across 53 countries, representing a variety of industries. And over the next 90 minutes, regardless of your industry segment or your location, we're confident that you'll find today's webinar of value. Now, before we get started, Richard Fisher, publisher inside GNSS, Inside Unmanned Systems, would like to take just a moment to welcome you and introduce our sponsor, as well as our main moderator for today. Over to you, Richard.
Thanks so much, Lori. On behalf of Inside GNSS, Inside Unmanned Systems, and today's sponsor, the Thales Group, I extend a warm welcome to our audience from around the world for today's webinar. We value your participation, and we're delighted you're with us today. Now, I'd like to introduce Ariane Roller-Ventique, Marketing Manager at the Thales Group, for some opening remarks. Ariane?
Well, hello all, and thanks for being online today, especially given the current context. I'm happy to say a few introductory words before handing over to the speakers. First, a special thank you to Inside GNSS, who have made this event possible, providing the best channel and audience for the messages we would like to share. As you may know, Thales is one of the leading players on the inertial system market. As a result, Thales is focusing on a new disruptive form of technology, microelectromechanical systems, or MEMS, and more specifically on silicon MEMS. This technology is said to be the great frontrunner on tomorrow's market, thanks to three key assets: smaller size, lower power consumption, and better price, all of which has led to Thales designing a brand new accelerometer based on silicon MEMS technology. And during this webinar, we will explain how. Over to you, Richard.
Thank you, Ariane. Now, I'd like to introduce our moderator for today's webinar, Alan Cameron, who is the Editor-in-Chief of Inside GNSS and the PNT Editor for Inside Unmanned Systems. Alan's covered the GNSS, PNT, and autonomous industries as a writer and an editor since 2000, focusing on technical issues around continuous, reliable positioning and navigation. Alan, welcome. The floor is yours.
Thank you, Richard. Thank you, Ariane. And thank you, everyone around the world, for joining us today. Thank you, of course, to Thales Group for making this possible. Well, I remember as if it were yesterday when Thales came into being, and I think Richard was there by my side. A long heritage with many other companies in defense and several forms of navigation, guidance, and control. Thales has established quite a place for itself at the top of the world's companies providing navigation. Now, we've spent, if you've been paying attention, if you've attended recent webinars, we've spent quite a bit of our time devoting attention to MEMS inertial, and specifically to MEMS gyroscopes. Today we are going to look at the other, or one other, significant aspect of MEMS inertial, and that is MEMS accelerometers with our panel. And I will introduce our panel individually as we get going. We're going to hear from Vivien Lagorce at Thales, Dimitrios Damianos at Yole, Développement, Edgar Hinüber at iMAR, Navigation, and Pierre-Olivier Lefort at Thales. But before we hear from each of these distinguished gentlemen, Lori, let's learn a little bit more about our audience.
Let's do that. So you should see a poll coming up on your screen. If you wouldn't mind weighing in, we'd love to hear from each of you. And the question is, what is your status in selection of accelerometer, and for which application do you plan to introduce it? we're asking that you just go ahead and select one answer. Responses are in early exploration without any specific application, in R&D and need accelerometer for civil or military airborne apps, in R&D and need accelerometer for land or naval apps, in R&D and need accelerometer for autonomous apps, or perhaps have an accelerometer solution and do not plan to change that solution. So it looks like 36% in early exploration without any specific application, 23% R&D and need accelerometer for civil or military airborne apps, 10% R&D need accelerometer for land or naval apps, 17% R&D need accelerometer for autonomous apps, and 15% saying have accelerometer solution and do not plan to change solution. So Alan, any thoughts here on this poll?
Well, I think everyone is just about where they want to be, which is in the right place, ready to learn more about the new possibilities of accelerometers, except for the 15% who do not plan to change. But I have a feeling that even they will learn something to their profit. A third of the audience is in early exploration, and the rest are in various fields. Of course, this is going to be of interest to Thales and all of us as to which fields they are in. I think everybody, regardless of your application, you're going to learn something to your advantage. We're going to hear first from Vivien Lagorce, who is the MEMS sensor project manager at Thales. He graduated in electrical engineering from Grenoble Institute in France and joined Thales Group in 2009. At Thales, Vivien has carried out the development of several power supply electronic products embedded in airborne applications, such as flight controllers, GNSS receivers, and inertial navigation systems. He has been in charge of their airworthiness certification process regarding European and U.S. regulations, and now Vivien is the project leader of the new high-grade accelerometer and gyroscope based on silicon microelectromechanical systems, in other words, SI-MEMS, and as you'll see frequently throughout the presentations, SI-A, or silicon based accelerometers. These sensors combine compactness with high-level performance. Vivien, please proceed.
Yeah, thanks, Alan, for this introduction. And thanks a lot to the webinar attendees. I'm glad to present you today the new generation of Thales high-grade accelerometer and how we're offering a user-friendly solution combining compactness and performance. First of all, let me introduce Thales and its experience in inertial technology. Since 1980, Thales is embedded in major civil and military programs requiring high-grade inertial systems. Our expertise is based on our technological knowledge with more than 1,000 patents. We provide inertial systems based on our own sensor developed and manufactured as ringing laser gyroscope and Panelists accelerometer, or also quartz MEMS accelerometer. In addition, our expertise is in GNSS allow to provide one of the most performant inertial systems. Today, we deliver more than 10,000 navigation systems per year and accumulate more than 300,000 MEMS sensors in silicon and quartz technology. Our MEMS sensor accumulate more than 1.5 billion of operating error and safety critical applications. Based on its strong experience in high-grade inertial product, we have developed a new generations of sensor. We propose to you today our new silicon MEMS accelerometer. We have developed a large portfolio up to 100 G of range and lower than 70 micro-G of bias with the same sensor size, which allow you to select the most appropriate sensor for your product performance, but also generate your own product portfolio by just changing the accelerometer versions. This new silicon accelerometer offering the best swap for this class of performance with only 6 cubic centimeters. You can integrate easily the sensor in your system and reduce the rate and consumption which one of the major challenges for new urban mobility has UAV, but also for climate change. To facilitate integration, the speed increment information is provided through SPI interface, which can be directly read by the processor of your system. This principle drastically reduces the duration of integrations and finally increase your competitiveness. Then, we provide you a sensor fully designed and manufactured in France, recognized for its high quality and engineering and industrial, then facilitate exportation. This new generation of accelerometer coming from several years of research to find the best silicon MEMS design. To provide you the best performance, Thales selects silicon MEMS technology using the differential vibrating beam principle to combine the highest range of measurements with the lowest bias. The differential principle allows to have a common modular rejection better than 10,000. You can see on the right side a simplified representation of the sensitive part of the MEMS. Both resonators are located at the middle of this active silicon layer of the MEMS. Each resonator is composed of a fourth amplification structure and a drive and sense electrode. The seismic mass is connected to each resonator. Then, when the seismic mass moving on the sensitive axis, the frequency of each resonator proportionately changes with the acceleration. To have better understanding of the principle, see the short movie. So, this movie represents the MEMS with another simplified representation. But you can see the mass, the seismic mass, at the middle, then moving up and down due to the acceleration. And two resonators with changing of the frequency proportionately to the mass moving. We have also integrate a custom active damping system here, which allow to improve performance under vibrations. Manufacturing of the cells is using only highly stable silicon and silicon oxide material, including the Thales patent stress isolation features for die assembly, located at the bottom silicon layer to link active layer to the packaging. All these principles coming from several years of research to provide the best performance of bias under all temperature range. This is a particularly important requirement, for example, in missile guidance application with high temperature variations. Even if the principle, the physical principle, seems to be complex, its use should remain simple for you. For that, we have designed the electronic to facilitate the communicate with sensor and its use. The user have to provide single 5 voltage power supply. It can program the sample rate up to 6,400 Hz, then read directly the calibrated speed increment through the digital output, which is a standard SPI interface. In order to be reused in place of other accelerometer in your system, we provide you analog output, which can be also used to perform your own speed increment treatment. Also, to allow you to have fast plug and play, the compensation parameter are stored in memory during calibrations in your facilities. Analog and digital temperature is provided for compensation. Then, in order to ensure of high level of reliability for safety, critical application as civil aircraft or new urban mobility or also autonomous vehicle, the sensor embeds built-in test functionality, which can also be used for maintainability to prevent any out of use of your system. Now, let me introduce our manufacturing line. Our silicon MEMS cell was designed by Thales engineers, then manufactured by Telecatronics. This collaboration from several years with one of the leader in French MEMS manufacturing, resulting in a high-grade MEMS accelerometer using a robust and standard industrial process. Once the MEMS cell is manufactured by Tronics, the sensor integration, calibration, acceptance is performed in Thales facility using a new smart manufacturing line, which have a production capacity higher than 30,000 sensors a year and allow to adapt to logistics to your needs, of course. Like we can integrate vendor managed inventories process to manage your stock easily. Finally, Thales guarantees your product availability and support throughout all your product life, however long. But performance and reliability of the sensor also result from a controlled development process to ensure of safety critical applications like civil aviation, autonomous vehicle, or also train transportations. Based on our experience in safety critical application, we have applied DO-254 aeronautic development methodology in order to prevent any potential failure. We have followed a rigorous methodology standard to trace any step of the development phase, from requirement capture to final verification of the sensor. For each step of development, an accurate documentation to justify the activities performed and their result is provided. This data package, including plans, specification, verification, result, will be available for the certification process of your product. Of course, Thales will support you during your certification process with airworthiness authorities. In addition to the methodology of the development, the sensor is designed to meet the high-grade inertial lifetime of 25 years and a reliability of 160 feet, which allow to be compatible with primary navigation channel for civil long-range aircraft. Finally, choosing Thales is not simply for its performance, for its high-performance sensor, but also for support from your sensor selections to your serial production, with a complete and accurate user guide to integrate our silicon accelerometer easily in your system. We support you for your integration system in order to find a well compromise to meet with your product objective. We support you in your certification process, as said, by offering engineering support and a full data package. Then we provide you a sensor coming from a qualified manufacturing line, which meets the most rigorous standard for this kind of performance. Finally, we will be your side anytime and anywhere thanks to our worldwide Thales networks. So, one more thanks for your attention and enjoy the next part of this webinar. I give you back the hand, Alan.
Thank you, Vivien, for that look inside the sensor. Now we know what we're talking about. I have a couple of questions for you, but I'll hold those for a little bit longer. We're going to look next at the market, the MEMS market. Following some questions, we'll take a look at some actual applications of the sensor and then return for a closer look at some of the specifications of the sensor. We're going to hear next from Damianos, a technology and market analyst, imaging and MEMS for Yole Développement. Dimitrios Damianos, PhD, joined Yole Développement as a technology and market analyst in the photonics and sensing division. He works every day with his team to deliver valuable technology and market reports, as well as custom consulting projects regarding the imaging and sensor industry, including photonics and MEMS. He holds a bachelor's degree in physics and a master's degree in photonics from the University of Patras in Greece. After his research on theoretical and experimental quantum optics and laser light generation, Dimitrios completed his PhD at Grenoble University in France in optics and microelectronics. He has authored and co-authored several scientific papers in international peer-reviewed journals. Dimitrios, tell us about MEMS history and market.
Hi, Alan. Thanks for the intro. Hello to everyone watching today's webinar. Thanks for tuning in from all around the globe. I hope you're doing fine. So from my side, I'll speak briefly about the inertial MEMS market and the MEMS accelerometers, just to put slightly into perspective the presentations from my fellow speakers. So Yole, for those of you that don't know, is a market analysis and strategy consulting company with activities in silicon technologies and high tech. So the applications that we monitor in Yole regarding the high-end inertial systems are mainly four high-end markets that you can see here. We have the industrial market with agriculture, robot navigation, UAV navigation, structural and machine health monitoring, pipeline monitoring for gas and oil applications, and the list goes on. Currently, we think it's the market with the highest growth opportunities in the future. Then we have commercial naval market with mostly the gyro compass and not finding application, which is critical for the navigation at sea. But we also have AUV, ROV navigation, stabilization of antennas or other critical platforms, SIP, tilt monitoring, etc., etc. Then in the commercial aerospace, inertial systems are used in flight controls as HRS, for example, or for aircraft navigation, for antenna orientation, in satellites, etc. And we see a growing trend and interest in micro nano satellites currently with that carry small payloads actually, which could really boost the inertial market since it would be a higher than usual volume application. And as you know, with the SpaceX's reusable rockets and now that the new space is coming, launching small satellites has become cheaper than ever. So we think there are some opportunities there for inertial systems. And remember, US now has a Space Force. So we think that there are some things that will develop in the future. Finally, defense applications need inertial systems, for example, in missile seekers for missile guidance, navigation of armored vehicles, military aircraft, defense drones, weapon turret targeting, etc. And in defense, actually, there is the resilient PNT, position navigation timing trend that is driving the use of these inertial systems, because you need to be resilient when there is no GPS and to avoid also some GPS jamming. So now each of these applications has its own requirements that can be the level of integration and the performance as well. And at the integration level, the systems can either use a standalone accelerometer, standalone gyros, or IMUs, INS, HRS, etc. So performance needs are also different. For example, you can use an IMU for navigating a ship and the same IMU for guiding a missile. So, I mean, SOC requirements are different, in-run stability, bias drift are different, etc. Now, let me focus slightly on accelerometers. There are more or less 4 families or detection principles that you can see here in the slide, and 6, let's say, accelerometer types. So MEMS are currently a very hot topic because they can be greatly miniaturized, and also they offer one of the most promising SWaP-C. So they gain a lot of traction in many applications. Regarding the accelerometer performance, high-end accelerometer performance, these are categorized in 4 main grades. The strategic, navigation, tactical, and industrial grade. And the 2 main parameters for this classification are day-to-day, bias stability, and scale factor stability. And the applications that I showed earlier actually can be categorized in one of these 4 performance grades. So as you can understand, they will need different silicon MEMS accelerometers or other kind of accelerometers. Without going actually into too much detail, yes, as I said, day-to-day bias stability refers to how stable the output of the accelerometer is over time, and the scale factor stability is actually linearity of the sensor. So silicon MEMS are pushing more the limits of their performance and have reached the navigation grade, meaning they can address most of the application. Now, as I said, accelerometers can be also integrated in IMUs. So when we see the whole pictures, IMU performances have really very much evolved during the past 15 years. Then they were not even considered high-end, but now they're moving towards to more critical applications. And MEMS-based IMUs are already used in tactical and industrial performance-grade applications, but also some MEMS accelerometers are used in navigation-grade IMUs that integrate actually non-MEMS higher performance gyro technologies. So let's say MEMS accelerometers are also more advanced in performance than MEMS gyro. And yes, finally, let me show you briefly the size of the inertial systems market. So when we talk about the high-end market, then all inertial systems at all levels of integration, like standalone, IMU, INS, etc., including all accelerometer and gyro technologies, represented the 3.24 billion market in 2019. dollars, yeah. Of that, the standalone silicon MEMS accelerometers were almost 200 million. We expect this market to grow up to 4.25 billion, of which $330 million will be for silicon MEMS accelerometers. So good growth opportunities, as I said, and the main growth drivers will be coming from industrial applications. And also just before closing, to put this into perspective, the inertial systems market for commercial applications, which, okay, it's not the focus today, but for example, for consumer, automotive, and medical, was 3.14 billion in 2019. Without going into much detail, we see that the sizes are similar in units, in value, sorry, but when we talk about the commercial market, we talk about billions of systems or units. So in the high-end domain, it's, let's say, in the 100,000s or maximum million range of units. And just to note here that the commercial market with combo sensors such as IMUs, they are slowly replacing the standalone inertial sensors as the packaging becomes better and costs come down while performances increase. So that was it from my part. Very quick debrief of what's happening. So I'll give back the mic to Alan.
Thank you, Dimitrios. To me, the most a lot of interest there, but salient point is MEMS accelerometers are actually more advanced than MEMS gyros. We've devoted a lot of attention recently to gyros, but we see here that accelerometers are actually more providing more capability and being integrated in navigation grade applications. We're going to pause for a few questions now from the audience. Vivien is the sensor, the silicon accelerometer. Is it available now?
It's a good question. Yeah, we are in an industrialization phase with the objective to qualify our manufacturing line, as I said before, to meet the industrial requirement necessary for this kind of sensor, like performance reproducibility or corner case detection, you know. So for now, sample will be available at mid-2021. And of course, we would be glad to discuss your need now.
All right, so conversations are open, and the sensor is coming very soon. Yeah. How do you qualify the sensor, Vivien?
Our sensor is qualified as a representative environment for long-range aircraft. As you know, we are an expertise in this kind of market, and so we qualify the sensor for these environments, which is a strong environment, like also for military environments. So for that, we perform several tests in different thermal, humidity, shock, IMI are applied directly on the sensor. But in order to have a good representation of the performance of the sensor, the qualification is performed on a representative population of the sensor to verify the reproducibility of the performance.
Okay. Laurie, for our next question, I think it would be helpful if we could go back to the movie slide in Vivien's presentation, because someone has asked about the seismic mass of the sensor. And if you can take us back to the movie slide, I think, here we go. and if we can even
Yeah.
see it going. Vivien, seismic
Yeah.
mass.
Yeah, so the seismic mass, what is the seismic mass? The seismic mass is the sensitive element of the MEMS. It is let free into the MEMS to moving under the acceleration detections. The seismic mass is linked to the resonator of two resonator. Then when the seismic mass moving under the acceleration applied to the sensor, the resonator will change the frequency. So the seismic mass is used clearly to detect the accelerations, in fact.
All right, thank you. A couple of questions for Dimitrios now. Dimitrios, of course, the question that comes up in almost every conversation nowadays, or a variant of it, did you take into account the impact of COVID-19 in your forecasts? And if not, how do you foresee that changing the market landscape?
Yeah, so in the market values that I presented earlier, no, we didn't take it into account. These are some results right before COVID happened, so around January and February. So the effect that we expect depends, of course, on the market and the end systems associated. So yeah, we expect an effect. So just to go maybe through the four main categories and four main markets. So military and defense, it's one of the foundations, let's say, for some countries like US and China. And despite the slowdown, the economic slowdown, we expect this segment to remain strong. But maybe have a slower growth than before, but still not any significant impact. For example, yes, for this year, the programs are there, the spending is going on, and maybe some deliveries could be slightly delayed since production is slowed down due to some disruption in the supply chain. Now, commercial aerospace, everyone knows, and hears and sees and feels it's the hardest hit segment. There were big supply chain problems in the previous months, and also reduced aircraft production is expected. On the other side, commercial naval market, not any significant changes expected, besides a slight decline maybe of some cruise ships and the usage of cruise ships. And in the industrial application side, maybe there will be a slightly negative impact on the train transportation, and also maybe some drilling and offshore applications, since oil and gas projects also postponed, in this volatile market. So actually we're trying to reevaluate the market, and according to some scenarios that we have made, we will update the numbers very soon. So yeah.
Yeah, that all makes perfect sense. A bit of delay, a bit of time to recover. Let's hope that we all recover and move on. One more question for you, Dimitrios. Which, in kind of slicing and dicing your data there, which applications require standalone accelerometers? And for those applications that use IMUs, how significant is the accelerometer portion of that?
But there are various applications. What I can think right now is mostly, let's say, industrial ones. There's machine health monitoring, like vibration monitoring, and for example, some wind turbines, where you need to monitor the turbine, the gearbox, the blades, also even some control of the tilt and the inclination of the tower. Also some train as well applications, such as train tilt, the monitoring of suspension, of positioning systems, etc., and also maybe some other inclination applications, such as in forklift and agriculture systems, etc. So in these applications, the most important characteristics of the accelerometers are the low noise and high bandwidth.
Thank you, Dimitrios. We've had questions for our panel. Now we have a question for our audience. Lori?
Sure thing. On the screen is that next question. Which class of performance would you be interested in for your applications? Bias composite less than 70 micro-Gs, bias composite between 70 and 200 micro-Gs, bias composite between 200 microGs and 1,000 microGs, or bias composite greater than 1,000. All right, well, we have 41% saying less than 70 microGs, 31% between 70 and 200, 17% between 200 and 1,000, and then 11% with greater than 1,000. Thoughts here, Alan?
Well, simply that the requirements are fairly high for the major part of our audience. I'm going to leave it to our experts from Thales to comment further later on in the program if they wish about this. We're going to hear next from Edgar Hinüber, CEO and owner of iMAR Navigation GmbH. He's going to tell us a bit about the applications of accelerometers in the field, of which he is a great specialist. Dr. Engineer Edgar V. Hinüber, as I said, is the CEO and owner of iMAR Navigation in Germany. He graduated from the University of Hanover in electrical engineering, control, and information theory with a diploma in 1989 in the field of machine vision, and a PhD in 1993 in surveying of industrial robots with inertial sensors. He founded iMAR Navigation in 1992 in St. Ingbert, Germany, and he has more than 30 years of experience in inertial solutions and technologies in defense, industrial, and surveying applications. Edgar, please go ahead.
Yes, thanks, Alan, for your kind introduction. Dear ladies and gentlemen, I'd like to welcome you to the next slides of this webinar. Now we will have a look to the requirements on high-performance MEMS accelerometers in the areas of navigation, stabilization, surveying, and control from the point of view of a system architect and inertial sensor integrator. We at iMAR Navigation have been providing standard as well as customized inertial solutions for more than 25 years to our customers worldwide. We are located in St. Ingbert, about 150 kilometers southwest of Frankfurt in Germany, close to the French border. We design and manufacture INS GNSS systems as well as gyro-stabilized platforms. With our high expertise, we attend to customer applications in surveying, marine, airborne, automotive, and mining areas, industrial and defense, on manned and unmanned platforms. iMAR Navigation has about 75 employees, including 38 engineers. The turnover last year amounted to about 18 million euro. This slide shows some application areas of inertial sensors together with two key requirements of accelerometers, which are major components of inertial measurement systems, besides the gyros, of course, and the GNSS engine. It is very important to distinguish between day-to-day bias and short-time bias stability. On this slide, we see typical requirements for several applications. As an example, in submarine or aviation applications, very high accuracy is required, while in automotive and commercial tasks, often a day-to-day bias of 10 millig or even higher is fully sufficient. This slide shows a few typical realizations from our product lines using high-performance accelerometers. For instance, stabilized platforms for camera and antenna operated on moving platforms, systems for airborne gravimetry to determine the value of gravity within micro-G accuracy, or very ruggedized systems, e.g. for drill head control. What are the performance requirements for precise navigation and precise tilt sensing? We have listed them here on this slide. A very low accelerometer bias is required and a good long-time stability over years. For an accurate and stable scale factor, we have the same requirements. Low noise is important for good navigation results and fast tilt sensing. High shock and vibration resistance and immunity is needed to minimize, for instance, rectification effects. High bandwidth, very small jitter, and the well-determined latency are mandatory for high-performance signal processing inside the INS GNSS systems. Mechanical stiffness and long-time stability to obtain best orthogonality after calibration. Deep self-testing capability and high MTBF of the sensors are crucial for designing and achieving highly reliable systems. And last but not least, a good synchronization capability as well as an integrated digitization helps the user to increase system performance, to simplify system design, and to reduce cost. So you see there are a lot of requirements which have to be fulfilled from these sensors. Just a short view on the data fusion. The slide shows very roughly where the accelerometers are used within the INS GNSS systems. Besides measuring and integration into acceleration to obtain the position, we have to take into account Newton's laws, which means that we have to compensate for gravitational acceleration, and we need additionally complementary sensor information to meet the long-term navigation and performance. For this purpose, the data fusion is used to enhance the good inertial short-term performance to long-term mission applications and to estimate and compensate sensor impacts like bias or scale factor errors in real time. Better day-to-day sensor performance and low sensor noise helps this data fusion to provide high performance results already within shortest time. Typical aiding sensors are, for instance, GNSS, odometry, or computer vision-based navigation. Now we come to the specific questions for the accelerometers. That means, why is a low accelerometer bias important? Let us focus on the impact on an accelerometer bias on position accuracy in inertial navigation. The bias is the first-order error source for a navigation system and of significant importance. A lower bias leads to a better performance in attitude, especially in free inertial operation mode or for tilt sensing. And a better bias instability in combination with a reasonable long-term stability allows the data fusion to estimate the sensor parameters faster. During short-term navigation, the position error due to an accelerometer bias increases quadratically over time. A 1 milli-G bias leads after 10 seconds to half a meter position error. And if you do this for 1,000 seconds, of course, you have already 5 kilometers errors. This shows why a very small bias is important. Of course, most long-term navigation happens on the Earth, which is a gravitational sphere. And here, the so-called Schuler oscillation fortunately limits the increase of the position error to a linear function. In the plot on the right side, we see the Schuler period with 84 minutes as well as the 24 hours oscillation. Both can be obtained from the motion differential equation. The plot gives the position error in meters over time in hours for free inertial navigation. As an example, we see a position error increase, for instance, for 0.15 nautical miles per hour for the Schuler and about 1 nautical mile for the 24 hours oscillation. And now we will give you some information how to estimate these errors. As a quite simplified sum rule, it is helpful to know that 100 micro-G accelerometer bias leads to 1,300 meters amplitude. And for this one, you can directly calculate what is the need of your accelerometer bias if you want to achieve a certain navigational error. Only to have it in a complete picture, also the gyros have an impact. So the position drift of Schuler is about 60 nautical miles per hour per 1 degree per hour gyro drift. This means not only the accelerometer is important, but also the gyroscope, and both has to fit together to meet the overall requirements of navigation. Why is a low accelerometer noise important? The low noise is important for the data fusion to allow a faster parameter estimation. The noise and the bias instability can be obtained from the Allen variance plot. The middle plot shows the typical Allen variance of the traditional high-performance QA2000 accelerometer, the Q-Flex from Honeywell. This is a benchmark for everybody who wants to make high-performance accelerometers. A state-of-the-art MEMS AHAS grade accelerometer is shown on the right-hand plot. The left figure shows the Allen variance plot of the new Thales MEMS accelerometer, and we can see that it meets the QA2000 benchmark for the highest demands in navigation. Finally, I'd like to explain why also a low latency and jitter of the accelerometer is very important for the system design and high-performance GNSS systems. Acquiring an acceleration measurement value with a delay tau will lead to a significant navigation error. The reason is that the accelerometer always measures two parts, the desired motion-induced acceleration itself and the gravitational acceleration g of about 9.8 meter per second square. To eliminate the gravitational acceleration from the desired motion-induced acceleration, the orientation, that means the attitude of the object, has to be determined precisely by the gyros at that time when the acceleration is acquired. It is also the jitter of the acceleration acquisition must be as small as possible. In other words, a jitter between orientation acquisition time and acceleration acquisition time leads to an error which is similar to a virtual time variant acceleration offset. As an example, to keep such virtual acceleration offset below of 60 micro G, any jitter shall be less than 20 microseconds. This new sensor fulfills this requirements. This is an important impact which is mostly overseen in system design, but of course gives you a big impact, especially navigating on the Earth. I'd like to thank you for your attention, and feel free to contact us with any questions. Back to you, Alan.
Thank you, Edgar. And we'll be back to you with a couple of questions that have come in during your presentation. But first, we're going to hear from Pierre-Olivier Lefort, MEMS expert and product design authority at Thales. Since 1990, Pierre-Olivier has led the development of MEMS technologies and several MEMS sensors for navigation, from air data pressure sensors to inertial grade vibrating accelerometers and gyroscopes. He has filled more than 20 patents in these fields and is also the author of several papers presented in inertial-oriented conferences. He's now focused on the market introduction of a MEMS accelerometer, affording an outstanding swap level. I wonder which one that could be. Pierre-Olivier, please tell us more about it.
Thanks, Alan, for the introduction, and welcome everyone to continue today's webinar on MEMS accelerometers. Following Edgar's talk related to the impact of accelerometers on inertial navigation performances, I will go into more detail to show how the design choices and the implemented MEMS technology of an accelerometer highly versatile, allowing to build smaller and highly accurate inertial systems. I wish to start directly on the main inquiries I've seen from the panel question and the webinar question. Here are the key characteristics for this family of silicon vibrating accelerometer. The features on the slide are the performance levels which are already reached on the first demonstration samples. And this is the median value for the different parameters, which means that 50% of the population have better performance than these figures. In fact, the association of the physical concept with an innovative silicon MEMS technology offers performances equivalent and even better than quartz vibrating beam accelerometer, with a lot of advantage about size and cost reduction coming from the silicon MEMS technologies. Among these figures and in relation with Edgar talk, I can highlight the unique combination of a very high acceleration range, up to 100 G, with bias and scale factor accuracy, allowing pure inertial navigation for several hours in operational condition on ground or airborne platforms. This kind of device is also very easy to use from mechanical and electrical point of view, and is designed to operate in user environment and combine high level of vibration and large temperature variation. This is always required for navigation application, as navigation objective is obviously to locate a moving platform. And for stabilization applications, a large temperature range is also very often uncontrolled. I mentioned before via temperature operating condition, and this slide details now the features which are important to use the accelerometer efficiently in these conditions. In fact, any sensor is more or less temperature sensitive, and the important feature is the ability to perform temperature compensation using an embedded temperature sensor as a reference and compensation coefficients which are stored in sensor memory. It is possible if the sensor temperature susceptibility is sufficiently low and smooth to be able to introduce efficient temperature compensation. Also, non-compensable phenomena like temperature hysteresis of the bias shall be below the required accuracy. The two upper charts here show that the sensor have response in line with the needs Edgar showed before. Left chart shows the residual errors after compensation for a group of 17 sensors with a mean value around 20 micro-G after compensation. The right chart shows also the response of one sensor under variable temperature conditions with 2 Celsius degree per minute temperature ramps. And we can even notice that this vibrating beam principle have an outstanding low scale factor error level in all the temperature range, with less than 2 ppm error after compensation, as represented on the lower left chart. And this is in fact the benefit from using silicon, which is a quasi-perfect monocrystalline material. Finally, on this slide, on the bottom right, we see the sensor output response just after power on, with a warm-up slope of the output lower than 2 micro-G per minute after 2 minutes running and less than 1.5 micro-G per minute after 3 minutes. Combined with the low noise level, this features a quick availability of the first aid information, for example, in low-seeker system. With thermal sensitivity, aging sensitivity is also one of the most important features, and it's very difficult to evaluate, in fact, for a new technology. Classical approach is to try to monitor response under artificial accelerated aging conditions. For example, high temperature aging or temperature cycling aging is performed, but acceleration factor is not always easy to identify, and more critical, it can be low. So it's very difficult to do accelerated aging. And to overcome this issue, since the very beginning of this sensor generation development, aging data have been accumulated on bias and scale factor drift using the first sensing elements engineering sample. And the charts here represent the parameter variation under natural aging for 38 days, but also for 2-year agings. For a 38 days period is typically representative of application allowing 1 month recalibration. And in this case, bias vibration is lower than 10 micro-G. And a 2-year period is more typical of application not allowing recalibration. And even in this case, bias variation remains lower than 50 to 80 micro-Gs. And scale factor aging on the right is also very low on the 10 ppm for 2-year monitoring here. Then a frequently published chart also is to quantify noise is the Allen standard deviation, the curve showing the noise component of the sensors. Here it is represented for 2 days output recording after lab temperature compensation. The straight line on the chart allows identification of velocity random walk, which is the important characteristics allowing efficient navigation algorithm conversions. And the instability can be read between time 0.1 and 1 day and is in the 1 or 2 micro-G range. Inertial navigation application have no real interest in lab condition, of course, and the chart here shows that the vibration and shock humidity have been taken into account in the sensor development. This device has the capacity to be efficiently compensated from vibration effect. Vibration sensitivity is here measured under 12G random vibration level on a set of 10 sensors, and the vibration induced error is typically 120 micro-G using nonlinearity compensation. This can also be converted into vibration rectification coefficient, sometimes reported in sensor datasheet. Here the vibration coefficient is in the 1 micro-G per G square range, which is quite low for MEMS sensor and even for, in fact, any accelerometer technology. Compensation is not always required for more quiet vibration environment, and the raw vibration coefficient is around 6 micro-G per G square. And for example, without compensation, a 2G random vibration will induce only 24 micro-G error before compensation. Shot sensitivity is also important for mission profile that are found, for example, in small systems like UAV. And bias variation after shock is represented on the chart on the right. And even after 100 shock, bias variations are kept below 50 micro-G. I show you just before the performances level achieved with the SEA accelerometer, which I think represents a real gap compared to available MEMS device. The heart of the sensor allowing these results is the sensing element built using a dedicated silicon technology. Silicon is well known for semiconductor manufacturing with smaller and smaller technology nodes down to a few nanometer critical dimension. But silicon is also an almost perfect crystal with impressive mechanical features. It's also a very good heat conductor, and this is important to manage thermal behavior. These characteristics and the ability to produce hundreds of devices on a single silicon wafer allows the availability of a sensor cell with highly competitive cost. On the picture here, we see some of the typical geometry used in the sensing element. Active layer thickness is in the 60 micron range, but resonator thickness is much lower, around the 8 micron. And the smaller dimension, the MEMS dimension, is the gap between the resonator and the driving electrodes, which is in the 3 micrometer range. And as Vivien mentioned, only monocrystalline silicon is used to benefit of 100% of silicon mechanical property. And this allows to build very good resonators for the vibrating beam with more than 100,000 quality coefficients, which is 5 to 10 times higher than for quartz resonators, which have been used on quartz vibrating accelerometers. And after now this overview of MEMS technology and accelerometer performances, I will present the sensor interface and integration future. From a mechanical point of view, one of the most common integration configurations is a 2-axle combination. associated to navigation-grade gyrometers. MEMS gyrometer, in fact, performances are today not sufficient to address pure inertial application, high-grade pure inertial application, and the SEA accelerometer should be associated to fiber optic or ring laser gyrometer for the moment. And the small vibration sensitivity of the SEA device will be very useful when associated to ring laser gyro, as their activation function will induce medium to high vibration level. And the low power is also useful to avoid overheating of sensitive optical devices. And as the sensitive axis of the accelerometers, represented here, is parallel to its mounting plane, it's possible to build the very flat triaxial configuration, like the one shown here on the slide, and only 24 millimeter thick triaxial assembly inside the 60 millimeter diameter cylinder is possible. From an electronic integration point of view, the main feature of the SEA sensor is the versatility of the output signals. The SPA line will be the preferred communication link to users' equipment, with access to digitalized velocity increment data and sensor temperature data. And communication integrity can be checked using CRC data, also available through the SPI registers. This electronic interface requirements could be compared to the acquisition electronics required for classical analog current output accelerometers, which require the use of high-performance analog-to-digital converter with up to 24-bit accuracy maintained over temperature and lifetime, which is a bit challenging. This means less than 1 ppm electronic accuracy. If digital output is used, we are in the discrete time regime. So it is mandatory to implement a synchronization function to have the same sampling time for each accelerometer of a triaxial configuration. And two modes are offered to define a speed increment sampling time. Either on the left, sampling time is defined by one of the accelerometer set in master mode, and the sampling signal delivered by the master being used by the two other accelerometers set in slave modes, and also sent to the user for synchronization with other device. And this is the left configuration. And on the right, more classical perhaps, the other modes is to have a sampling time defined by the user and sent to the three accelerometers set in slave mode. In any case, latency can be as low as 400 microseconds, depending on the data rate used, and the jitter is in the sampling time is lower than 5 microseconds. Finally, high reliability is also a key characteristic for any application, and especially for inertial systems when often used for safety critical operation on ground and airborne platforms. From our experience in delivering MEMS sensors in 1995, MEMS technology allows to reach very high reliability level as there is no friction, very limited movement amplitude, and only a few assembly technology. This is especially true with the vibrating beam principle. In the sensing element here, under both normal operation but also power off operation, there is no friction and no contact between silicon beams and masses. On a safety point of view, the issue is a bit different, and it is likely to avoid undetected failure. For this need, several built-in test features are introduced to monitor electronic health, but also to monitor the MEMS resonator health. And dedicated features are also included to limit single event effect from atmospheric radiations. So now this is the end of my talk, in which I intend to show you what can now be expected using MEMS technology for accelerometer. MEMS technology are still young, but now give also access to high-grade inertial navigation for accelerometer, and probably, I think, for gyrometer in the next decade. Thank you for your attention. Back to you, Alan.
Thank you, Pierre-Olivier, for that in-depth look at the accelerometer. We now know exactly what it is capable of. Still, there are questions, and we'll turn to those questions in just a moment or two. First, we have a question for you, the audience. Please let us know what you think about this.
Okay, on the screen is our third and final poll for today. Except for performance, what is the other key requirement your accelerometer should have? Small size, easy to communicate without exportation constraint, civil certification data package, or large portfolio for a same size of sensor. Well, 39%, our majority here, saying small size, 23% easy to communicate, 24% without exportation constraint, 7% civil certification data package, and 6% large portfolio for same size sensor. Alan?
Well, as indicated in the SWAP acronym, size comes first. I think this is borne out by the survey here that getting performance in a small form factor is the leading consideration. However, communication and export controls also factor in, with the others being less significant. We're going to turn now to questions from the audience. And first for Edgar. Edgar, harking back to your performance, what are the key advantages from a system designer's point of view in using this Thales MEMS accelerometer for high performance applications?
Oh, there are a lot of advantages in this technology, I think. One of the key points is that you do not have to recalibrate a system within a short period. Therefore, the long-term stability of parameters seems to be very interesting for us. Another point is from the signal processing. On the one side, if you take a Q-flex traditional sensor, you have to take into account that the power dissipation inside of this sensor depends on your acceleration. So you have a current there of about 1.3, 1.4 milliamps per G. Therefore, the heat dissipation depends on the measured acceleration. And this, of course, is a big advantage of this MEMS technology, that the power dissipation is more or less independent from that one. So it gives you a much better capability to make modeling the temperature behavior. The scale factor, of course, is important. It will not help if you have an accelerometer which has a few micro G offset, but about 100 or 200 ppm scale factor error, because if you go into the field of gravity, then you see this as a bias. Another important point from our point of view is the integrated digitization. Again, if you take a traditional most accurate Q-flex, then you have this 1.3 milliamps per G, and you have to take care to get it quantized. And there you need something about 22, 24, 26-bit digitization. And this is sometimes a challenge if you want to make a very small design. So also this seems to be a quite big advantage. And of course, if you want to make the avionics systems, if the sensor itself has already a DAL A certification or is designed according to the DO, then it is definitively an advantage.
And from the integrator's point of view, Edgar, how difficult is it to replace a traditional accelerometer with this MEMS accelerometer?
Yeah, it depends, of course, on the system design. So if you have a system design where you have a traditional accelerometer and you want to replace it, then you have a very easy interface in this accelerometer. On the other side, you have to look if you have a digitizer in your own system to replace it. So there's some work, there's some engineering work, but such a sensor which comes with an SPI and digitized data makes it definitively much more easy than to use any other sensor. So I think the design looks very user-friendly from our point of view.
Very user-friendly. Pierre-Olivier, again from the aspect of integration, on what kind of material can the accelerometer be mounted? For instance, aluminum, stainless steel, composites?
Yes, so often it's a critical point as we can have thermal mismatch between the sensor and the equipment. And in this case, this can degrade, for example, misalignment of the sensor, or even sometimes induce a bias deviation. And to avoid this, the sensor includes a metal frame designed to allow quite high thermal expansion mismatch between the user interface and the sensor mounting hole. And this allows stress release and avoid any misalignment drift during temperature variations and temperature cycle. So any material, in fact, with up to 25 ppm per Celsius degree linear thermal expansion can be used. This includes aluminum alloy, stainless steel, some composite. So most of the material which are used classically on IMUs.
And is it possible to connect several devices on the same SPI line?
Oh yes, yes. Of course, the SPI electrical interface is using a three-state driver for the data out signals. So the clock, data in, data out signals can be shared between several devices. And one slave select signal is required for each sensor. So for a three-axial configuration, 3 lines are required for the slave signals and 3 lines for the shared signals. And of course, communication shall be time multiplexed to address each sensor after this.
All right, a question for Dimitrios. Why is the silicon MEMS commercial sector projected growth so much lower than the high-end market?
Yeah, so actually it's simple because in the results that I presented about the market, the commercial market, these are very recent. So we have already included the impact of COVID-19 at the end markets like consumer automotive. So as I said, we have accounted for some scenarios regarding its end market. So in Yole we have, let's say, made 3 basic scenarios: the worst, middle, and the best case scenario, depending on various hypotheses like I don't know, supply side measures, like government policies, etc., etc. So we use a combination of these scenarios for each end market to account of what will be most probably going to happen. So there is a big effect in automotive, for example, that we expect car sales this year to drop. So and this will the pre-COVID levels will come back in like 2 or 3 years or more. So this has really an impact on the commercial market and on its growth rate. And also there is another thing that I mentioned maybe very slightly in my presentation, is that also the standalone sensors in the commercial market are being more and more replaced by combination of sensors. So let's say more towards the IMUs because the packaging becomes better, the costs come down, and the performance is increased. There's also a big price pressure from the OEMs in the commercial market. So That's why maybe the growth rate seems lower than the high end. But as I said, you should maybe check, I don't know, our website will have a communication maybe a month of the effect of COVID also in the high-end inertial market. So yeah.
Price pressure from OEMs. Who would have thought that that would be a factor? Vivien, excuse me. Vivien, a question for you. Is this a single axis accelerometer that we're talking about?
Yeah, I just confirmed that all the presentation, yeah, definitely yes. We haven't said that, we haven't precise that it is only single axis accelerometer, yeah.
Okay, and a question for Edgar. You mentioned the difference between short-term bias stability and day-to-day bias stability for different industries. Can you elaborate a little bit on the difference between these two specifications?
Oh yeah, both specifications are often mixed by the users. You have to consider that the short-term bias stability is a value which is obtained at constant temperature. It tells you how long a sensor keeps a constant value over time at constant temperature. It's a so-called Allen variance plot where you can get it. The day-to-day bias is a totally different thing. It tells you if you switch off, switch on, if you change the temperature and so on, what is the bias overall. That means if you have a navigation system and, for instance, you have no aiding, then you have to rely on the day-to-day bias. If you have a GNSS aiding, for instance, then the short-term bias stability can help you because you can estimate this bias much better than the day-to-day bias. But take into account if there is a temperature gradient, this looks totally different. Therefore, do not take only the bias instability or bias stability, but look also to the day-to-day because this is the starting point of every data fusion. This is for all the industries, independent on the applications.
Thank you, Edgar. And now a question for Pierre-Olivier. The quoted performance for the accelerometer, the silicon accelerometer, is this specification for under temperature control, or is it temperature compensated?
The normal use of the sensor is to perform temperature compensation. So the sensor provides the temperature measurement with either a digital output and analog output. Then the user has to perform the temperature compensation using this information of temperature and also temperature coefficient, which are stored in the sensor memory and which can be read through the SPI line. This is a polynomial temperature compensation model, and which is very classical for compensation, and third order compensation for bias and second order for scale factor, for example. There is no temperature compensation inside the sensor itself because it does not have real added value, because generally users still have to compensate misalignment drift with temperature, and this cannot be compensated in the sensor itself because it's a single axis sensor. So in any case, the user has to perform temperature compensation for this parameter and to identify, of course, before the misalignment temperature drift. So it is a temperature compensated sensor and not temperature control sensor with stabilized temperature, which is much more complicated and power consuming technology.
All right, we're getting deep into the details now. Pierre-Olivier, if you would please, another question for you. How does the active damping work? Is the proof mass underdamped, and what is the resonant frequency of the proof mass motion?
Yes, interesting question. This vibrating beam principle, in fact, is an open loop. We have an open loop device with a resonant frequency of the proof mass defined by the mechanical design. So the resonance frequency is quite high because it's a small structure and it has been designed to be very high to avoid much of the vibration spectrum which can be found in inertial applications. The resonance frequency is higher than 4,000 hertz, and it is damped, for example, to improve dynamic response, and it is damped using electrostatic damping because the structure is under vacuum, and it must be under vacuum to have good resonator properties. So we cannot use the, for example, gas damping, and it is damped using electrostatic forces to reduce the mass resonance at 4,000 kilohertz.
Aha. So we have taken a deep look at the high-performance accelerometer in navigation, stabilization, control, and surveying. I'd like to thank all of our panelists and give them each a chance to pose a concluding comment. Let's just go around the virtual room. Vivien, a final word from you.
Yes, it was a really interesting webinar for us to prepare, and I think for the attendees to understand and to more understand what was the high-grade accelerometer, and most important point, what was the Thales high-grade accelerometer proposed to you. With a small size, with a high performance, facilitate for integration also. So I hope that whole was interesting for the attendees. Yeah. So thanks a lot for the attendees today.
Thank you, Vivien. Dimitrios, concluding comment?
Yeah, just to say thanks for everyone that joined and followed the webinar. It was really interesting to present with all of these exciting developments going on in the accelerometer market. And from my side, seeing the applications and markets and seeing the actual performances of the new sensor, this was really interesting. And I hope it has helped our viewers maybe decide on their application, or maybe decide to acquire this new sensor. I don't know. Hope it was informative for everyone. So yeah.
Thanks. Very much so, and thank you for the market perspective. And Edgar, thank you for the application perspective. A wind-up word from you.
Yes, also my thanks to everybody for the interest and questions. It's a complex area, and we hope that we could make it a little bit more understandable what are the key issues of these sensors. And if there are any questions later on, please do not hesitate to contact us. Thanks again.
Yes, as Edgar said, we remain open for questions, and the respective experts will follow up with you with the answers. And speaking of respective experts, Pierre-Olivier, a final word from you.
Thank you, Alan, and I hope this presentation has convinced everybody that the MEMS technology is in a big progress, and this is true, I think, for accelerometers, and probably will be also true for gyrometers, for MEMS gyrometer. And thank you to Edgar, Dimitrios, and Alan for your help. And It was a pleasure to present you the new SEA device.
I'd like to thank all of our panelists again for the perspectives they have brought to this. I know from my point of view that it is helpful, even if I've seen the information once, to see it again and again, because it sinks deeper each time. And the advances in MEMS technology are quite astonishing. When I started out in GNSS many years ago, this was quite unforeseen. It was at the very low end, and it's moved very rapidly in the last 5 years, I should say, into high performance. And the new applications that MEMS technology is opening up, specifically in accelerometers, as we have seen today, but across inertial technology, really quite astonishing. And they are changing the landscape of what is possible with positioning and what is possible in cooperation with GNSS. Thanks again to Thales for making this webinar possible. Thank you to all our attendees around the world for joining us. We encourage you to watch your email inbox for a message about the presentation. It will be made available to you. Lori will tell you just how in a moment, and you can review it again. You can share it with your colleagues, and of course you can contact the experts for further answers to your questions. Thanks again. This is Alan Cameron signing off from Inside GNSS. Lori?
Yes, I echo all of the thanks and acknowledgments that Alan just gave. And most importantly, again, thank you all for joining us. This is Lori Dearman saying, hope we see you on the next one. Bye for now.